Hey, Precalc
Section 2.
of Chapter 6.
Vectors. Dot product of vectors even. So these are the properties of the dot products of vectors. And all these properties over here might not make a whole lot of sense right now, but as we start going through dot products, they will.
Hey, let me throw this out.
All right.
In Section 1, we talked about
Vectors.
vectors, and we talked about how we can add two vectors together.
Right, head to tail.
We talked about how we can multiply a vector by a scalar.
Right.
But we said we can't really multiply vectors together. What we have instead is this thing called the dot product.
Yes, that is correct.
And it has this dot here, and so when you see u dot v, we're not saying u times v, we're saying do the dot product of these two vectors. So it's kind of like our version of multiplication.
Four vectors.
And it has some cool properties, like what we were saying.
I just said all that.
Yeah.
You
No, you didn't
repeated
say-
everything
no.
almost I just said.
No, you didn't.
Okay.
Should we go back and listen?
We'll run this after we.
Okay.
Okay.
Okay, so
So there they are.
there they are.
And they look kind of
commutative.
Yeah.
And this one's a new one. No, that's kind of normal. Like u times u is normally u squared, but there's an absolute value situation going on.
Right, because it's distance. With vectors, everything's a distance.
0 dot u is 0. That's kind of like multiplication.
Right, scalar.
This is kind of like the distributive property,
Right.
but with dot product.
Right.
This right here is like an associative multiplication-y thing.
Yep. That's what it is, because it's a constant times the vector dotted with another vector. So it's like a scalar, vector, dotted, keep going.
Yeah. Basically, it just means that you can pretend like the dot product is multiplication if you have something really complicated going on, like as far as the order you do it.
Right.
Yeah. Okay.
But the dot product's a dot product. You got to follow the steps
This
for
right
that
here.
puppy.
This is the steps.
Right.
U dot v, you take the first component of each and multiply it together.
Yep.
Plus the second component of each.
What you just said is brilliant.
Okay, so
let's try it.
Let's try it.
Okay.
So 3 times 5 plus
plus
4 times 2.
Yeah, and look, 3 times 5 is a product.
Oh, it is a product.
Yeah.
And so is 4 times 2.
Yeah, 4 times 2 is also a product. So we're producting numbers between vectors. That's the product part, and the dot is the symbol in between.
Okay. Yeah, it's a dot product. Okay.
Dot product.
The dot product of these two vectors is 23.
You should always get
a number. Not a vector.
Correct.
A scalar, you might say.
Yes, a scalar.
Okay. So, and it could be a positive number, a negative number, or 0.
Right.
Anything goes.
Any
number goes.
Okay, any number goes.
Okay, so this would be 1 times negative 4, because you do first times first plus second times second.
Negative 2 times 3.
Work that out.
That would be negative 4 minus 6. Big negative diez.
Which is 10. I thought you didn't know Spanish.
I know just a little bit.
Now, we also have a different way of writing vectors where we use i's and j's instead of having it where it looks like a point. So it's still the same situation, just only take the numbers.
Yeah, this is not going to end up being an I squared situation.
No.
You still have to have I as your vector thingy, but when you dot product it out, it's just the numbers.
Yes. You just take the numbers out. It's kind of like we're switching this to component form.
Yeah, 2
and
negative 1.
And then doing it.
Right.
Because really component form is better.
Right.
In some ways.
Yeah, there you go. So 2, 3, negative 1, negative 5.
Negative 1, negative 5.
Right. There we go. Okay, so 6 plus 5.
6 plus 5.
That's 11.
Yeah. Cool beans.
All right.
All right. Property 2, which is up above you, so you don't need to write it down, but let me just rewrite it real quick. What was property? Property 2 is u dot u, where these are vectors.
I love the little vector symbol, actually, by BT
Do you?
Dubs.
I bet you've said that before.
I might have. Now, remember that...
these absolute value bars, I said they were absolute value bars in the previous example, but that's the magnitude of u.
Right, magnitude,
So
don't forget. We've talked about this previously, magnitude. We're just... But now, instead of the magnitude overall between two vectors, which is what we did, we're going to look at the magnitude of one vector.
Yes, the magnitude of one vector.
By dot producting.
By dot producting. So what we can do is we can take this property 2 and square root both sides, and so that gives us the magnitude of u by itself equals
square root of the dot product.
Of the dot product of them together.
How about that?
Okay, so when this problem says use the dot product to find the length of the vector u, it means that we need to do the dot product of 4 and negative 3 with itself. Okay, and then when we get our answer, we're going to square root it.
Yeah.
So
I totally agree.
Okay, well, the dot product is first times first plus second times second.
Yep, there you go.
And then we'll square root it. So 4 times 4 is...
That's 16.
Okay, and negative 3 times negative 3?
9.
So 16 plus 9?
It's totes 5.
And that means we get 5. Now, you may notice when you're doing this that this is basically the Pythagorean theorem or distance formula, right?
Right.
4 times 4 is an awful lot like 4 squared. Negative 3 times negative 3 is an awful lot like negative 3 squared. They're just trying to point out to us, the book is, they're trying to point out to us that, hey, this is another way of going about it.
Right. Because it's a vector.
It's a vector.
It's a little bit of a different shape than what we've done before.
Right. And I could go on and on about how useful this is in higher math, but none of us want to hear about that. Including
me.
Yeah, so just trust me, there is a reason why they're showing us this. It's just not relevant to us whatsoever.
At this moment in time.
Hey there. Example 3. Now we've got these nice handy-dandy formulas to help us find the angle between two non-zero vectors. So assuming our vector isn't a zero vector, which is a silly vector to use anyway.
It's basically like a nothing.
Like a nothing vector. It's like
the nothing from the Never-Ending Story.
I have no idea. But that's a tangent that I don't know that we need to go on.
All right.
Okay. So the angle between two non-zero vectors, you can use cosine of theta equals the dot product of u and v over their magnitudes multiplied together. So on top, we're dot producting. On the bottom, we're going to multiply the magnitudes together.
And remember, magnitude is distance, and so those are going to be positive, okay?
Yeah.
Which is one thing that is helpful about its notation. It looks like absolute value bars, and the absolute values are positive.
But we're finding magnitude because these are vectors.
Right.
And so if you were to solve for theta, that would mean you were taking the inverse cosine of this junk right here.
Or arc cosine.
Or arc cosine if you wanted to call it that. So
we got
a couple examples here, and we're just going to find the angle between the vectors. If it doesn't specify whether it wants degrees or radians for the angle,
I feel like in this case degrees are okay because I understand about where 15 degrees is a lot better than I understand 0.379 radians.
Okay, but if it's specified, it would just mean, because we're probably going to use our calculator on these,
it
would just mean a change of mode. Whatever it wants you to put it in, that's what mode we need to be in.
And these angles should always be greater than 0, less than 180.
Because if it was bigger than 180, we could talk about
the angle going
the other direction. Okay, cool beans. So it would be the difference between talking about this angle versus the angle on this side.
We're going to talk about yes.
Yeah. Okay. So what we need to do is we need to basically do 3 things. We need to find u dot v.
All right. You get on that.
We need to find the magnitude of u.
Get on that.
And we need to find the magnitude of v.
If you can get on those 3, I'll just punch in what you find out into my calculator.
Great. So u dot v is first times first. So 2 times negative 2 plus second times second, so 3 times 5, which gives us negative 4 plus 15, which is 11.
So that's going to be on the top there.
Okay. The magnitude of u, remember we do a Pythagorean theorem situation with that, basically, with the sides, because it's in component form like that, which is the handiest form of all.
Yes. Now, when you're working this out, I highly encourage you to put into your calculator the square root
of whatever.
Whatever times the square root of whatever as your whole denominator.
Right, because we want as little rounding as possible. So right here, 2 squared is 4, 3 squared is 9, so we get square root of 13.
So put that square root of 13 into your denominator.
Absolutely. Best idea ever.
Well, it's a pretty good one, yes.
Okay, and Pythagorean theorem for the magnitude on this one, negative 2 squared plus 5 squared.
So that would be 4 plus 25, which is 29.
So square root of 29. And so when we set this up to put in our calculator, theta equals the inverse cosine of 11 is on top, and the square root of 13 and the square root of 29 are on bottom, being multiplied together. One thing you can do whenever you put this in the calculator, because it's kind of tricky if you're not paying attention.
Yes, it is.
You need to have either parentheses on the bottom, or technically, because we're multiplying, we could put those under the same square root. We could do 13 times 29 under the same square root.
That is true. That is very true. But don't decimal them out and round and then put them in. It's the
that's silly.
Big deal. Okay, I punched in on my calculator. I got 34.5.
Why'd you do inverse sine?
Gosh darn, suck a monkey nugget, stinking poopsies. Okay, hold on.
I feel like we should cut that out or like bleep
no, hold on.
what you just
All
did.
Right.
That's ridiculous. Like in Harry Potter. Ridiculous.
Ridiculoso.
And any of you who had boggarts behind you, I just banished or vanquished them or whatever.
55.492 degrees. And so there we go.
55.492?
492.
Can we check and see if that's right real quick?
Yeah, let's have a quick check.
Because we've had some calculator issues.
We have in the past, but we're not going to talk about it. Hey,
good job.
Is correct.
That's
Thank
correct.
you. Thank you.
I had complete and total faith in you,
Except
as I'm sure all of our viewers did as well.
So why would you say it like they don't?
Can we not fight in front of the kids? Should we not argue about this right now? U dot V, magnitude of U. Oh, real quick though, let's look. Does it make sense that this angle right here is 55?
I mean, it looks like that could work.
Looks like, because it looks like it's less than a 90
degree
angle.
Yeah, it looks like less than 90, and yeah.
So that's what we just found. We found that angle right there.
Yeah, sounds good.
Okay, so right. U dot V. So now we're doing this problem. So first times first plus second times second gives us
-2 minus 3,
which is
-5 Reno.
Magnitude of U, so 2 squared plus 1 squared square rooted is square root of 5. And then -1 squared plus -3 squared, and we're going to square root that as well. So that's 1 plus 9, which is 10, so square root of 10. And then we're going to put theta equals the inverse cosine.
Got it, K-Steve.
-5 over square root of 5, square root of 10.
You don't have to bring it up and say it like that every time.
Okay.
But I got 135 degrees, which as it turns out is correct.
Oh, nifty.
Yeah.
Now, because that is a value on our unit circle, we probably could have done this by hand if we had actually multiplied this out and got square root of 50 on bottom, and then simplified or rationalized. We probably would have ended up with like a negative square root of 2 over 2 situation, and then we could have said, oh, that's 135 degrees.
But you know what, that's okay.
And that's this angle right here. So what we were saying is that finds this angle, not the angle on the other side, which is bigger than 180. So that's interesting. It finds the smaller angle.
It does. It finds a smaller angle.
The other way would be 360 minus 135. So
right, but we don't want that one.
But if you did, you could find it.
Yeah, okay.
Okay. Vector projection. Now, this is one of them, their real-life application-y kind of things.
Which means it's pretty darn hard.
Well, relatively, yeah, I would say. Yeah, it's a little bit harder maybe
but
than
it's totes doable.
Yeah, so we have this picture here in your notes that talks about what a projection? A vector projection,
what
it shows. So if they give us a vector U, then the projection of U onto V.
In other words, if you were to shine a light like the sun on top of the green vector, how much it would just cover up the red part of the blue vector.
Right. So this whole long vector is V, isn't it?
Yes.
Okay, so from here to here, this is all V. So we are taking U and we're projecting it onto this other vector V. That's what vector projection does. And in a second, we'll talk about what that's used for in like real physicsy life. But this is the formula we use. This is the projection of U onto V. Notice that it's U onto V, and that U's the big letter and V's the little letter, because that does matter.
It does matter quite a bit, actually.
What they'll ask us to do in some of these problems is they'll, like this one down here, they'll ask us to write U as a sum of two orthogonal vectors. One of them will be the projection of U onto V.
And an orthogonal vector, just a real quick memory aid, is two vectors that are perpendicular.
Right, that they meet at one of them 90-degree angles that
one
we're
of them 90-degree
fond
things.
of. Okay, so what we're saying is U is going to be the sum of two vectors. We're going to call them U1 and U2, where
U2.
U1
in the name of love.
Yeah. U1 is the projection.
That could be the code word.
U onto V. What's the code word? In the name of love?
Yeah.
Okay. In the name of love, like this?
In the name of love. You got to sing it. You want the full credit, you got to sing it.
I mean, yeah, you do.
Right.
Right.
By
okay.
Singing.
U1 equals projection of U onto V. So that means that U2, because here they're giving us U. These are all vectors.
Those are all vectors. And so we can do a little bit of algebra to work backwards now.
Right. We'll have U.
We'll know what U is. We're going to be able to
get projection of U onto V. So U2 we'll be able to find by doing U minus U1. Right? Yeah. That's the way this is going to go.
That looks great.
Projection of U onto V and then subtract. So the projection of U onto V, we have to find the dot product of U and V to put on top. So here's U and V over here. Let's just dot product those real quick. 6 times 5, right? First times first, yep, plus
30.
Second times second.
I believe that's correct. So
2 times -5.
Right. So 30 minus 10.
Which is 20. That's what goes on top of our fraction here. On the bottom, we have the magnitude of V squared. So the magnitude of V
squared, which is just the part under the radical.
Right, because if you have a square root and then you square it, those cancel each other out. V is 5 squared plus -5.
And holy smokes, if you don't put -5
in the parentheses,
you're going to have a magnitude of 0. And look at the picture.
There's not a magnitude of 0.
There's nothing there magnitude of 0.
So make sure you put the negative in parentheses or just leave it out. Just that negative doesn't need to be there. It's going to be squared away. That gives you 50. Okay, remember we squared away the square root. So it's just 5 squared plus -5 squared, which is 50. And then we have this vector V. So the projection of U onto V is the dot product, which is 20, over the magnitude squared, which is 50, times our original vector V. Okay. Where...
There they are.
There they are. There's the colors. Got it.
There we go.
Okay. So now we would distribute.
Yeah, a little distributing. You could even, if you were like uber cool, yes. If you were uber cool, you would be like, that's a 0 over 0, and them things cancel out.
All right. That's 2/5 times 5 comma -5, which that's kind of convenient because the 5s will cancel, leaving us with 2 comma -2.
Yeah, I believe that's correct.
Okay. So this is the projection of U onto V, which is U1. Okay, that's the first thing that they wanted us to find. We need to find now another one to go with that. And basically we're finding...
the dotted line.
The dotted line, right. This would be like U1.
U1's the red part.
Oh, U1 is the red part, and now we're finding U2. So because we want the two vectors to add together to get this last vector.
Right.
So U minus that one there.
Right.
So 6/2 minus what we just got.
2 -2.
Gives us the other vector. So 6 minus 2 is 4.
Right.
2 minus a -2 is 4.
Yeah, that's it. That's the right answer. There's your...
So that's that vector.
Which vector is that one?
I'm not sure which one that is.
Which one is that one, K-Steve?
Eudos.
In the name of love.
You should have changed part of that to Spanish.
I don't speak Espanol very well.
True story.
Hey, jawbone. All right.
Go away. Yeah, there you go. Example 5, vector projection. And that.
Write it as a sum, though, right?
Then
write it as a sum. So we would just add.
U equals
vector
2, -2. Plus
vector 2,
comma 4.
There you go. Game over now.
Okay.
Dunskies.
Okay.
In the name of love.
Please, whatever you do, do not forget the code word for this video. In the name of love. go. By all means, go ahead.
How can you use one of them vector projection thingies?
Like in real life?
Yeah.
Well, let's look at this example. Using vector projections to find force. If you are, let's say you've got a box and
you will learn how to use vector projections.
Box and a flat surface, and you're like pulling in a certain direction, but it's not like even with your surface, then the projection of U onto V is the effective force pulling it forward. Like the actual force you're pulling with.
You are going to work the rest of this problem.
Well, I am going to work the rest of this problem, but it's not because you just mind tricked me. Oh, I'm a Toydarian. Mind tricks don't work on me. Only money.
Darn it. Where's your wings?
I'm also not blue. Okay, number 6. Rowan is sitting on a sled on the side of a hill inclined at 45 degrees. The combined weight of Rowan and the sled is 140 pounds. What force is required for Marin to keep the sled from sliding down the hill? Now, did this actually happen? Because I believe those are your children's names.
We don't actually have like a hill, and I think Marin would have shoved him instead of held him. So
no, not completely.
This is totally fiction.
Okay, but with your kids' names.
Yeah, kids' names.
Okay, so we're trying to figure out the force that's going to keep the sled from sliding down the hill, which means that we need a vector projection. Combined weight of Rowan and the sled, that's 140 pounds. So that is the force that's pulling them down, right? Mm-hmm. Is 140. So we're trying to figure out what's the force that's going this way from that. Right. Like if you're being pulled down by gravity and stuff, with 140 pounds.
Is there more than gravity at work here?
It feels like sometimes there is. Okay, gravity's pulling you down towards the ground at 140 pounds, which means since you're on a hill, that some of that is going to be directed down the hill.
Right.
And so she's having to pull this way.
Right.
So she's having to pull this way with a force equal to what is going the other direction.
Down the hill.
So this right here, that should be the projection of this one onto this one?
Yeah.
All right, so we have that formula that we used, U dot V over V squared times V.
Right. That's it. That's it right there.
So what's U and what's V in this case? We only know right now
Well, we don't know much.
We know 140.
We know 140. We also know though that we've got an angle of 45 degrees in there. So could we use that to maybe find a directional vector, a directional unit, our unit directional unit, our
unit,
one of those unit
we
vector
can figure
things.
out what a vector in this direction,
yeah.
Right? So because is this angle also 45 degrees?
I mean, if gravity pulls straight down, doesn't it have... That's 45 degrees, doesn't that have to be?
I think you're right.
Yeah, every now and then I am.
Every now and
Not too often.
Okay, so we've got the vector pulling down, which is, it's pulling down, so that's 0, negative 140. And if you don't understand why that's what this vector is, think about it for a second. Okay, not you, them. Oh, I think you understand.
I mostly get it.
Okay, pause the video and then see what happens. We want a unit vector, which means we're going to do 1 times cosine...
45.
45? But that's not the angle, is it? Because it's to get around.
No, because it's still going to be just the angle in between there.
You sure?
Like if you look back on the other problem, it was the angle in between that's going to make the difference.
Okay.
So, yeah. And sine 45. Yeah, there you go. There you go.
Okay, so we know actually what those are without even having to do anything.
Square root of 2 over 2.
That's just a unit vector in this direction.
Right.
Okay, so we want to... Which one of these is U and which one of these is V?
Let's go with the 140 part being the long guy that's on the top projecting down. Right?
So which one is that?
So that was the long one coming down.
No, yeah, this is this one, but is that U or is that V?
That's the long one that's coming. It's the long one that's coming down.
But for our formula, is that U or is that V?
I believe that it is. I think that's the U one. It's projecting. No, U onto V, right? That's U.
Okay, this is U, and this is V.
Right.
Because we want to put U onto V.
Right.
Which is our unit vector. Okay, so we need the the dot product of U and V. So that's 0 times square root of 2 over 2, which is just 0, plus negative 140 times square root of 2 over 2. So that's negative 70 square root of 2. If you cancel out a 2 from each.
Did you
like that?
That's good recovery. Good recovery.
I did it on purpose. The magnitude of v squared. Wait, this is a unit vector. So the magnitude of a unit vector is 1, and 1 squared is 1. How convenient.
Wow.
I wonder if that's why we picked the unit vector.
Indeed.
So that's negative 70 square roots of 2 on top over 1 times our vector v, square root of 2 over 2, comma square root of 2 over 2. So you distribute, and you get negative 140. No, negative 140 over 2. See, square root of 2 times the square root of 2 is 2. And the 2's would cancel out, so that's negative 70.
Negative 70. Negative 70k, Steve.
Got it.
It's negative 7 on both those things.
Right, because they're the same. I see what you're doing there. But what's important here, which is, and so I kind of disagree. I feel like this angle really should have been a different angle. Like, we're doing a trig thing, so we probably should have made it like 225. Okay, but the reason it doesn't matter is because we just want the magnitude, so the signs don't matter.
Signs don't matter.
And so 70 squared plus 70 squared is, and then square root it.
Yeah, I'm on that. 70
square roots of 2
plus 70 squared is it's going to be 9,800.
Is that it? 9,800?
Yeah, 9,800. But I haven't square rooted it yet. I can't rationalize on this puppy, so.
Well, it's a real world problem, so let's just get the decimal
98.994.
98.994. How many decimals do we want?
I don't know.
Don't we want 3? We always tell them 3.
0.995.
Okay.
Bingo.
Pounds.
Of force,
so
holding the sled up.
Little Marin is having to pull with almost 100 pounds
but not
of
quite
force
100
to keep her brother from
sliding
down the hill.
Right, that is
head
correct.
First.
Yep. So now, this is a tricky problem.
It is.
And one of the best ways to help understand what's going on with this problem is to turn your sheet of paper over, rewind the video, and see if you can work this problem out on your own, and then start the video when you need some help.
That's a great idea.
And then after you've worked it maybe a couple times, some stuff will start to creep into that brain, and it'll make sense.
Yeah. Okay, cool.
Yeah. Too bad we didn't have Victor, you two in there. In the name of love.
All right, so we are going to talk about work.
Yes,
which is a physics thing. And in physics, you might see it written out as work equals force times distance. And that's true. We're working with vectors, so we're going to kind of adapt to that.
And your physics teacher also may use a different tip or trick or something like that with vectors as well. As long as his math is correct, we're
fine.
okey-doke.
Right, yeah. So this right here that's highlighted that you can't really see, this is supposed to say work equals the vector for force
times
dot product
times
the distance from A to B, the vector from A to B.
Right.
Okay, if you dot product those, that actually works out to be the same as doing
because it gives you a number.
Right, and then another way of doing it, depending on how they give us the problem, is we could find the magnitude of the force
times the magnitude of AB times the cosine
of the angle.
Right.
So it kind of depends on what they give us. If we can find the two vectors, if we can find the vector for the force and we can find the vector for the how far we've gone, then we can just dot product those.
I agree 100% with you.
So for this problem, example 7.
You will work example 7.
I will work example 7. Okay, find the work done by a 10-pound force acting in T direction. Thanks, Hazelwood, for that typo.
Nobody can prove that that's my typo
1,
right
2, and moving an object 3 feet from 0, 0 to 3, 0. So what's happening is that based on the information they told us,
we've got this like 10-pound item.
We're trying to, but no, not 10-pound item, a 10-pound force.
Yeah, that's what I said.
No, that's not what you said. We're going from 0 to 3. Okay, so our vector AB is...
This is an easy one. I know what this one's going to be.
Okay, what is it?
It's going to be 3, 0.
3, 0.
Oh,
okay.
Yes, I knew it.
Because it's this vector that's going along this horizontal line here. It's only going 3 to the right, and it's not going up or down.
Right.
Okay, the other one's a little trickier. We've got a 10-pound force acting in the direction 1, 2. But I don't know if you know this, but the magnitude of 1, 2 is not 10.
What?
No, it's not. So
Dang
we
it.
need to figure out what the vector for real is that would have a magnitude of 10 in the direction of 1, 2.
Oh,
so
there we go. Okay.
2 ways to do this. One is using unit vectors.
Right.
The other is to find the angle for 1, 2.
And then multiply by 10.
And then do 10
times that.
10 times cosine. Plug it into that formula like we did in 6.1. What do you want to do? Unit vectors or the other?
Let's just use unit vectors,
okay.
And we'll broaden our horizons.
Okay, so we need to find the unit vector in the direction of 1, 2.
Right, so that means we need to divide that vector basically by its magnitude.
Right, its magnitude is 1 squared plus 2 squared is 5 underneath the square root. We're going to multiply that into 1, 2.
So it would be 1 over square root 5. And it would be 2 over square root 5?
Right. And the beauty of unit vectors, here's the handiness of them, is that if we just put that magnitude in front of in front of this and then distribute it through,
it gives us that 10 force.
That's the force vector.
That is friggin' awesome.
Okay,
so that's going to be 10 over root 5 and 20 over root 5.
Right.
Yes.
Root 5. Okay, so this one is our F vector.
And we've got the AB vector.
So now we just need to dot product them.
Wow. One of those dot product parts is going to be totes zeros.
True story.
Mm-hmm. You will finish the rest of the problem.
I'm just gonna finish up the rest of this problem, Mr. Hazelwood. So that part's 0.
30 over root 5. But I don't really know what 30 over root 5 stands for, so...
I haven't the foggiest idea. And this is a real-world problem, so we want real-world decimals.
The answer to that is 13.416.
I think that's 13.416. And this is work, which is in foot-pounds. Now, that's like this weird unit, which is like just for work, but... Think about it. We're doing force times distance. We just did it a weird way. Force is in pounds normally, and distance
don't you have newtons running around
feet.
Sometimes with that stuff?
With force, yeah.
Force
is either in newtons or pounds.
Yes.
But in this case, it was in pounds. So,
okay.
And then we multiplied it by a distance that was in feet. So foot-pounds is our
That's what you got to have for your units.
So happy 6.2.